So for our last video, let's talk about the names and formulas for binary ionic compounds. And so with this is just how we name some of our ionic compounds. And that's what we're going to focus on for this video, is just naming different ionic compounds. Now remember, just a reminder, ionic compounds, remember these are the ones that occur between a metal and a non-metal. So that's the only type that we're focused on for the last bit of today. Ooh, not name and compound. Metal and non-metal. Now, a couple kind of quick reminders about this. And so first, in order to become the most stable, elements form bonds. And when they form these bonds, this is how or what creates our compounds. And so that's the first important point. And so remember, when elements are forming these bonds or forming these compounds, all elements want to have 8 valence electrons. And so that's the key. And the way that they get those valence electrons, or to have 8 valence electrons, is through the charges that we showed you, that we talked about earlier with the periodic table. So those typical charges, like the alkali metals or that group 1 always forming a +1 charge, it's because they lost 1 electron, which means that it then goes from having a total of 1 valence electron. It then loses that 1 valence electron, so it has a full 8 again. And so that's the big important thing. Now with ionic compounds are an electrically neutral compound that is composed of a specific ratio of our oppositely charged ions. And so the idea with this ratio is the fact that the positive charge and the negative charge have to cancel each other out. Or if you added them together, you have to get 0. Now, the way that this works is that as one element is gaining electrons, the idea is that the element it's bonding with then has to lose that same number of electrons. So if one element gained 2 electrons, that means the other element that it's bonding with had to give up 2. And so with this brings up our first type of ionic compound, known as binary ionic compounds. Now, binary ionic compounds are just composed of only 2 elements. And so that's the big thing with this. And so let's talk about our rules for writing out our formulas of our ionic compounds. So the first step is to write out the symbol and the charge of your cation. Now, when we say the symbol, we mean the abbreviation that's given on the periodic table. Then we write out the symbol and the name of our anion. And so remember, our cation is the positive thing, which in all cases will be the metal, or polyatomic ion, which there's only one of. And then the anion is the other thing, and this is our nonmetal or polyatomic ions, which we'll talk about later. Now, if these charges are not balanced, this is where we then do this process known as crisscrossing the charge. And so by going through this process of crisscrossing the charge, we then write them as subscripts, but without the plus and the minus. And so after this, we rewrite the formula with the subscripts, but without the actual charges there. Now, an important note here is that if a subscript is 1, then we don't write it. Now, we should also make another note for ionic compounds in particular, and that is, if you can reduce the subscripts, you reduce. Now, it only applies to our ionic compounds. This doesn't apply to other types. So if you can reduce the subscripts, do it. All right, so let's look at our first example here. We have barium oxide. So we look at the periodic table and we find the symbol for barium, which happens to be Ba, and it has a +2 charge. Then we do the same thing for our oxygen. So since it's oxide, that means it's oxygen, and oxygen is in the column that has a -2 charge. So when we're writing out our formula now, notice the +2 charge from barium and the -2 charge from oxide will cancel each other out if we combine these two elements. And since they cancel each other out, that means that we don't have to worry about the crisscrossing part. It's just our formula for barium oxide is BaO. All right, so let's look at another example. This one is magnesium fluoride. So for magnesium fluoride, we have magnesium, which is Mg, and then we look at the periodic table and see that it has a +2 charge. Now we go through and do the same thing with our fluorine, and fluorine is all the way in group 17, which has a -1 charge. So notice here, our charges aren't balanced. If we add +2 and -1 together, we still have +1. And so this is where the idea of crisscrossing the charges comes in. And so when we say we crisscross the charges, we bring the 1 down for magnesium, and we bring this 2 down for fluorine. Now, when we do that, remember we rewrite the formula, but excluding the +2 and the -1. And remember, if the subscript is a 1, we also don't write it. So that means that magnesium fluoride should be MgF2. All right, let's look at another one, calcium phosphide. So calcium is Ca, and it's got the +2 charge. Then we have phosphide, which is just phosphorus, which happens to have a -3 charge. Now again, since the +2 and the -3 don't cancel each other out, we crisscross them down. And when we do that, that gives us our formula Ca3P2. All right, and our last one, we have iron 3 oxide. Now remember, with this Roman numeral, that Roman numeral is telling us the charge of our iron. So that means iron, which is Fe, has a +3 charge. And then we have oxide, which again is just oxygen. And so we look, oxygen is -2. So we crisscross those charges down. And when we crisscross those charges down, that gives us a 2 for the iron and a 3 for our oxygen. So our final formula for iron 3 oxide is Fe2O3. All right, and fun fact for iron oxide, this is also known more commonly as rust. So fun tidbit there. So that's the rust that would be like on your bicycle or on just random things outside, whatever might be rusty. That's what it is, iron oxide. All right, so let's look at our next step, which is our rules for naming our binary ionic compounds. So as we're naming our ionic compounds, our step is to first name the two ions. So we name the cation first, followed by the anion. Now we always do this process. So we always list the cation first and the anion second. Then remember, if we're talking about Roman numerals, we use Roman numerals with all of our transition metals. And that's how we identify what the charge is. So just like our last example was iron 3 oxide, and it told us the 3 as Roman numerals, we have to do the same thing. And so let's look at this. First up, we have MgCl2. So Mg is our cation, and for what it's worth, it's always cation listed first, anion second in your formulas. So first up is Mg, and so we look at the periodic table, and it happens to be just magnesium. Now, when we're naming compounds, yes, that magnesium has a charge, but we don't have to worry about including the word ion. So for the second part now, we have Cl2, and so we look at the periodic table, and we see that Cl is chlorine. But remember, Since in this case it's bonded, that means the chlorine is charged. So if it's charged, that means it's not just chlorine, but chloride. All right, let's look at another one then. We got Na2O. And so we look at the periodic table to see what Na is. And as we're looking, we spot it all the way on the left side, and it happens to be sodium. And then we look at the second part, so just the O, and hopefully by now we've caught on that O is the symbol for oxygen. So this is sodium oxide. And then our last example in this is we have K3P. So we look at the periodic table and find K, and it happens to be also on the left, right next to or right around our sodium, and it happens to be potassium. Now, when we look, we go find P, which happens to be phosphorus, but remember we changed the ending to "ide," so this is potassium phosphide. All right, so this is how we name our ionic compounds or our binary ionic compounds. Now let's talk about what happens when there's transition metals involved. Now remember, the key is the fact that the overall charge of the compound is always neutral. And so if it's always neutral, that means that we have to look at the charge of the charge in the subscript of our anion, and that tells us we can figure out what the charge of our transition metal is. So let's look at this one. For example, we have Fe2O3. Now you can't just trust reverse crisscrossing. It doesn't always work. And so we have to look at the charge of our oxygen. Now, according to the periodic table, oxygen's charge is -2. Now, if oxygen has a -2 charge and our subscript here tells us we have 3 of them, that means that we have a total of -6 charge. Now, the iron has to balance it out. Now, so we look at our irons, and for our iron, we have 2 of them. And so it just kind of turns into a simple math equation as 2 times x has to equal +6. So what does that mean x is? Well, we divide by 2, and that tells us x has to be equal to 3. So that 3 represents then the charge of our iron. So that means that for our overall formula here, it should be iron, and then since it's a transition metal, we use our Roman numeral. So our Roman numeral of 3, and then oxide. All right, let's look at our next example. Here we got CuCl2. And so we look at the charge of our chlorine, and chlorine has a charge of -1. And again, we have 2 of them. So we have -1 times 2, giving us a total negative charge of 2, which means that the copper, or the Cu, has to balance it out. Now, since there's only 1 of them, there's no real math involved. If the total negative charge is -2, the copper has to be +2. So the formula for this one is copper 2 chloride. All right, and let's look at this last example here. We got SnCl2. And so just like our last one, since the Cl is -1 and we have 2 of them, that means the total negative charge is -2. And so the tin, to balance it out, if we're looking at it, since there's only 1 of them, the charge has to be +2. So this is tin 2 chloride. All right, so now that we've talked about this, let's talk about what happens when we have our polyatomic ions involved. And so this is our names and formulas for our ionic compounds containing polyatomic ions. Now, these are known as ternary compounds, which means that these are compounds containing 3 or more elements. And that means that in order for this to happen, they have to contain at least 1 polyatomic ion. And so that's the only way that we can get these ternary compounds is through the use of our polyatomic ions. And so for this actually happens to be the really easy part. With using polyatomic ions, we just go through and we write out the name of the cation found in the compound first. Then we write out the name of our anion found second. Now, the important thing with polyatomic ions is that we don't change the ending. And so we don't have to worry about changing endings to ides or anything like that. It's just, if something is like sulfate, it's just sulfate. So with that in mind, go ahead, remember our polyatomic ions list is in the commit to memory page. So take a second, find that, pull that out, so that way you can look at it as we go through our next couple examples here. All right, so first up, writing out the name of our cation. So we have NaNO3. So we look at our cation, which is the first thing listed, which is Na, and we look at the periodic table, and this is where it's sodium. Now we have to look for the next part. And so don't worry about charges or anything like that. Just look at that polyatomic ion list or the commit to memory page and find NO3. And so once we see the name of that, we see that it's nitrate. So this compound, NaNO3, is sodium nitrate. All right, let's look at another one. We got BaOH2. So Ba, let's find it on the periodic table. And this happens to be barium. Then we go look at our polyatomic ion list for OH. And hopefully we see it, and we see that it's called hydroxide. So this compound is barium hydroxide. All right, let's look at another one, CuSO4. Now Cu, as we're looking at this, remember this is one of our transition metals, which means that it does need a Roman numeral as we're writing out this name. So once we see Cu and we find it, it's listed as copper. Now we're going to just do copper. We're going to leave a space for our Roman numeral. Now let's go look for SO4. And on that list, SO4 is listed as sulfate. Now the important thing here is what is the charge of the SO4? So when you're looking at it, you should see that it says SO4 and it gives you a little -2 in the top right-hand corner. So that means that the charge of the sulfate overall is -2. And since we only have one of them, that means that the Cu, on the other hand, has to be +2. So 2 is our Roman numeral. And now let's look at our last example on this page. And this is Mg3PO42. Now remember, we don't have to worry about the subscripts at all yet. We just have to look at the names. So Mg, we check the periodic table, and we see that it is called magnesium. And then we look at our commit to memory page to find PO4. And this happens to be phosphate. So this is magnesium phosphate. All right, and this brings us to kind of our last little bit here, which is essentially going the opposite way. And so this is taking the name and writing out the formula. So this is similar to what we've already talked about. Our first step is to write out the symbol and the charge for our cation. Then after we write the symbol and charge of our cation, our next step is to write out the symbol and the charge of our polyatomic ion. Now, just like before, if the charges aren't balanced, we balance the charges, and you can do this by either crisscrossing or writing them as subscripts. If the polyatomic ion has a subscript, this is an important part, we put parentheses around the ion and write the subscript on the outside of the parentheses. So let's take a second and look at what that actually looks like. And it actually happens on our last example here. Actually, it happens on examples 2 and 4. So hydroxide is just OH. But since there's 2 of them, we put the OH in parentheses and the 2 on the outside. Now, the same thing happened in example 4. We had PO4, but then we put parentheses around it and put the 2 on the outside, indicating that we have 2 PO4 molecules attached to our magnesiums. So that's the important part of putting parentheses around them, because if we'll just use our last example here, if you didn't, all of a sudden it looks like Mg3PO42. And there's a big difference between 2 phosphates and a magnesium bonded with phosphorus bonded with 42 oxygens. So that's why those parentheses are there. All right, and so that brings us to our last step. And our last step is to now just rewrite the formula with the subscripts. So exactly like what we were doing before when we were writing out the formulas. And so let's look at some examples here. Our first one, lithium cyanide. So we first write out our cation, lithium, and it is Li with a +1 charge. Then we have cyanide. And so cyanide, we look on our list, and this is Cn, and Cn has a -1 charge. So these charges cancel out at the very beginning, which means that lithium cyanide is just LiCN. All right, let's look at another one. Our next one happens to be barium chlorate. And so we look on our periodic table, and we see barium is Ba, and it belongs in the alkali earth metals, or that group 2. So we label it as +2. Then for chlorate is ClO3, and it's got a -1 charge. So just like before, to balance out the charges, if barium is +2 and chlorate is -1, we're going to need 2 chlorates to balance out the bariums. So that means that our formula is Ba, and then our chlorate, which is the ClO3, should be in parentheses with a 2 on the outside to balance out the charge. All right, let's look at another one, aluminum sulfate. So aluminum is Al, and it's in group 13, which means that it has a +3 charge. Then we look at our list and find sulfate, and sulfate is SO4 with a -2 charge. So now, when we are looking at balancing out the charges, if we wanted to, we can either crisscross, which would tell us that it is Al2, and then in parentheses, we have SO4, 3. All right, so there's aluminum sulfate. And finally, our last one, we got calcium phosphate. And so calcium, we look it up on the periodic table. We see that it's Ca, and it gets a +2 charge. Then we do the same thing with our phosphate, and phosphate happens to be PO4, and phosphate has a -3 charge. So in order for those charges to cancel out, they both need to add up to 6, because that's the lowest common multiple between 2 and 3. And so if that's the case, that means we have 3 calciums. So we have Ca3. And then for our phosphates, since they have a charge of -3, to get to 6, we would need 2 of those phosphates. So that means that in parentheses, we have PO4. And then outside our parentheses, we should have a 2. Ooh, I don't know where it went. Well, hopefully it stays that time. All right, so that's it for our video today. Tomorrow we'll talk about naming our last 2 types of substances. See you guys on the next one.